Okay, Ohanian 13.75 from homework number 12 says that you have a stick that's hanging about a pivot at one end, so we'll assume it's at the very end. It's a thin rod. It has a mass M and a length L. Okay, and it's just hanging there at rest. When you throw a ball at it, a ball of clay of mass little m, I like to write my big M's with little feet so you can distinguish them more easily. Okay, so you throw a ball of mass little m at it with the velocity v. The ball hits the stick and sticks to it, so you have a completely inelastic collision, and that causes the combined system to swing up to some height h, just measured vertically above the original position. Okay, and you're asked how big is h? How far up does this swing in terms of the big M, the L, the little m, the velocity, and of course the acceleration of gravity g. Now here we have a collision and then a swing. So you're tempted when you say how high up does something go, at least I hope you're tempted to use conservation of energy and say the energy before it starts swinging equals the energy after, and using gravitational potential energy, mgh, you'll be able to figure out this height, and that's fine, except energy isn't conserved in an elastic collision. So we have to analyze the collision separately from the extra part of the motion at the end when it swings up. And how do we analyze collisions? We say collisions are short, so delta p, translational momentum, has to be 0, but in this case, it's not translational momentum we're worried about. Okay, it's going to be angular momentum. And so there are no external torques because you're swinging about the pin, but also because it's so short, then for the same reason momentum's conserved during a collision, angular momentum's conserved too. Okay, so angular momentum is conserved, says that L naught equals L final. So what's L naught, the original angular momentum? Well, this is a point particle moving with a velocity v with a moment arm. Now, although remember the r vector from the pivot to here is this, all we need is the component of the r vector perpendicular to the velocity vector. That's m r perpendicular v. And of course, that's also r cross p, where you'd say r is this vector, p, which is mv, is that vector, and the cross product would be this, and the sine of theta. But that would always just, again, be this distance, just r perpendicular to v. Okay, and r perpendicular to v is just the length L of the pivot stick, so that's just mvl. That has to be equal to the final angular momentum. Well, what's that? Now you have a system that's combined, a point particle at the end and a stick. It's a rigid body, so we'll treat that as an I omega instead of a point particle formula, a mass of a point particle, RV. So we need the moment of inertia of the combined system. Well, part of that system is a long rod of mass m and length L about its end. We worked that out in class. We also worked out the moment of inertia about the center of our rod, which is 1/12, but when you do the same integral about the end, it's 1/3 ml squared. Another way to get this is to say, well, the moment of inertia about the middle is 1/12 ml squared. That's in our formula sheet, and use the parallel axis theorem to see how that changes when you move the axis around. So that will work also, as we're just looking this up in the formula sheet for the text. You don't have to work it out from scratch. So this is our capital M. Put the little foot there to make sure you know it, plus the little mass of the ball times L squared, because it's a point particle rotating a circle of radius L. So its moment of inertia is just the sum of m sub I, r sub I squared, or ml squared in this case, times the omega after the collision. I won't bother labeling omega final or initial because there's only one omega to worry about. What's the angular velocity of the combined rod point particle when it starts swinging? So we can solve this for omega just after the collision. Just after the collision. It's also just before upward swing. It's just omega equals, solve for omega, setting this term equal to this term. These two are equal to each other. Okay, so solve that for omega, and we've got MVL, little MVL, divided by 1/3 capital M L squared plus little m L squared. So we're partway there. Now we know what the motion looks like just after the collision before it starts swinging, and we can switch to conservation of energy principles to see how far up it will swing. So I'm going to do something that might be a little confusing when I apply conservation of energy. There are two forms of energy. This will be kinetic energy. For omega, remember, kinetic energy equals 1/2 I omega squared, and it's now a rigid body. Okay, and we also have gravitational energy. Gravitational energy in general is mgh, but I'm going to define actually a pair of zeros for where I want to calculate h, because this is the general formula. For the ball, this is also correct for the ball, the potential energy of the ball. If the stick rises by a distance h, and I define potential energy of gravity initially to be 0, then the position of the ball after the swing, or at the high point of the swing, is just little mgh. But for the stick, it's a little bit different, because if the end of the stick goes up a height h, hopefully you could see the center of mass. The end of the stick goes up a height h, the center of mass goes up only half as far, because it's got half the length. Okay, and so I need to write this as capital mgh over 2 would be the final potential energy of the stick compared to its original gravitational potential energy. Okay, so the final energy of the system when it's swung up to its maximum height is just gh, that appears in both terms, divided by little m plus capital M over 2. Now I can put everything together. And I could say that the original energy of the system is U naught, gravitational, which is 0, plus the original kinetic energy, which is 1/2 I omega squared. Okay, and that's just equal to 1/2. We've got the moment of inertia above is 1/3 capital M L squared plus little m L squared. And omega, okay, what's the angular speed? The angular speed is going to be mv L quantity squared divided by 1/3 capital M L squared plus little m L squared. In case you don't remember where this omega came from, it's what we calculated up here for just after the collision, which is just before it starts rising in height. Okay, so we've got this formula, which we can then simplify because we have this in both expressions. Okay, so we can remember this whole thing is squared. I forgot that. It's omega squared, so this is squared, and this is also squared. Okay, so this cancels out that, and we're left with E naught, okay, equals 1/2 m squared v squared L squared divided by, that comes from this term, divided by 1/3 m, capital M, L squared plus little m L squared. That's this term after you cancel this term with the squared part of that. So that's the original energy. We also need the final energy when it's risen as far as it can and comes to a stop. But that's what we worked out up here. It's got no kinetic energy at that point. So the final kinetic energy is just this factor GH times little m plus capital M divided by 2. These two have to be equal. Okay, and now we just have to solve for h. So we're just going to take this and divide both sides of the equation by g and this expression. And so we're left with h equals 1/2g. That comes from dividing both sides by this g. So it's 1/2g times m squared v squared L squared divided by 1/3 capital M L squared plus little m L squared. Okay, And then I have to also divide both sides by this expression, so it's also little m plus capital M over 2. And the only other thing I'm going to do to simplify it is just divide out the L squareds, because that appears in everything. Okay, it appears both up here and down here in this expression. So we can simplify it, although it's still not all that simple, that the height is 1 over 2g. I'm glad to see that bigger g would mean less height. That makes sense. M squared v squared. So more initial momentum in the little ball means more height, and that also makes sense to me. 1/3 capital M plus little m. So more mass means less height, and with this additional factor too, 1 over little m plus capital M over 2. And we won't try to simplify it anymore. That's the answer.